Hello, welcome to today's video. Today I'm gonna discuss about Monte Carlo pricing of vanilla call or put options. Now I will try to answer an interesting question. How many parties are needed to price vanilla options using Monte Carlo? As we all know, for vanilla options, the payoff is very simple. For example, call option, the final payoff at expiry is maximum S minus K0. The well-known Black-Scholes formula is very widely used to price it. Black-Scholes formula is analytical formula, which means there is explicit formula and functions you can call to get the value. You can see it's SND1 minus K e to negative RT ND2. So if you put arguments into the Black-Scholes formula, you can get the fair value. One of the most important functions that is used in the Black-Scholes formula is this n, which is the cumulative distribution function of standard normal distribution. So you can see, in order to get a very accurate and fast Black-Scholes value, you have to calculate this n very accurately and fast. So one interesting question is actually this n, interestingly, is not explicitly given. There is no explicit formula to exactly calculate this function value. It must be calculated numerically. So one interesting question is, what is the cost of calculating this Black-Scholes formula? From this Wikipedia, you can see there are a lot of numerical methods to calculate the cumulative standard normal distribution function. Actually, there are various ways like numerical integration, Taylor series, asymptotic expansion, or continued fractions. So in summary, numerically, the cumulative distribution function of standard normal is approximated by simpler functions and therefore computationally efficient and accuracy. It can be very highly accurate, for example 8 or 16 digits. So these are generally enough for practical uses. Okay, so now we know that Black-Scholes is a very efficient and accurate way to get the vanilla option price. Now let's discuss Monte Carlo simulation. Before I discuss that, for Monte Carlo pricing derivatives, Paul Glassman's book, Monte Carlo Methods in Financial Engineering, is a very classic book, and I recommend everyone who is interested in financial engineering to read that book. Okay, so back to our today's topic. The general principle of Monte Carlo simulation or pricing is: one can approximate the integral by average. So assuming that we want to calculate an integral of fx from 0 to 1, the integral value is alpha, but we don't know it. So numerically, if we want to numerically calculate it, we can use this formula. So 1 over n summation of f of ui. So we sample a uniformly distributed random number ui and sum all of them and do an average. This will give you an approximation for this numerical approximation for this integral. So what does it mean? Well, geometrically, when you are calculating the integral of fx from 0 to 1, what you are doing is you are calculating the area formed by 0, 1, and fx. And your Monte Carlo simulation, what your Monte Carlo simulation is doing is you are trying to use the rectangular summation, the rectangular area summation to approximate the area, the true area. Why is the case? Because if you take a look at the calculation formula, so if you put 1 over n inside, this f of ui is just the function value at ui. And if you multiply by 1 over n is the rectangular width. If you time by the fui, which is the height of the rectangular, this will give you the area of the rectangular. So you sum all the area of the small rectangulars. So you're trying to approximate the area by rectangular summation. Okay, that is the general principle of Monte Carlo simulation. So how is this related to derivatives pricing? For derivative pricing, actually, generally it reduces to computing the expectations, which is then an integral of payoff function over a certain probability space. And that is why Monte Carlo simulation comes to play a very critical role in derivatives pricing. Let's take a look at how Monte Carlo can be used to price vanilla options. Assuming we are pricing a vanilla call option, the final payoff at x bar equals t is maximum s minus k, 0. So what is the fair value of the call option at today, t equals 0? So derivatives pricing theory tells us that the fair value of option at t equals 0 is the discounted expected future value. So you can say the fair value is an expectation of your payoff function over the stock price distribution. As long as we know the final stock price distribution, we can calculate the expected value of the payoff function over it. And then discount back to today gives us today's fair value. So you can see. So graphically, it looks like this. So initially we start from t equals 0. We have a stock price S. Then the stock price will diffuse into the future. So if the stock is in the future, the only thing that we can characterize it is distribution. As long as we know the distribution, we can calculate the expectation over the distribution space from the strike price k to infinity. And so actually it should be starting from negative infinity to positive infinity, but stock price is positive, so it can start from 0 to infinity, and we know when the stock price is less than strike price k, this payoff function is 0. So finally the integration is from k to infinity. According to Black-Scholes formula or Black-Scholes assumption, the final stock price is having a known distribution, which is geometric Brownian motion. So this integral is just the payoff function integral over geometric Brownian motion. So what we are doing is we are doing an integral over this shaded area. To price vanilla call or put options using Monte Carlo, actually there are two ways. One is directly use the final geometric Brownian motion distribution. The final stock price ST can be written as ST equals S0 into mu minus half sigma squared T plus sigma WT. This is the final stock distribution. Here, WT is random. It's a random variable. It has the same distribution as square root t times z, where z is the standard normal random variable with mean 0, variance 1. So how can you simulate the distribution of ST? You can simulate a standard normal random variable, then multiply by square root t, then times sigma, then plus times this do an exponential, then times S0. This will give you the ST final distribution. This is the first method. The second method is actually Black-Scholes formula is implying that the stock is following this stochastic differential equation. So you can start from the stochastic differential equation and do the discretization numerically. So dst equals mu st dt plus sigma st dwt. So you can discretize it directly by, st plus delta t minus st to discretize this dst. And mu st dt is delta t and plus sigma st dwt. So here the random number is dwt. It's having the same distribution as square root delta t times z, where z is the standard normal random variable. So what are the differences of the two methods? The first method, you are starting from S and directly simulate the exact stock terminal distribution. But in the second method, you are simulating the whole path and approximating the stock terminal distribution rather than exact stock terminal distribution. So you start from S, and then from S at 0, you get S at delta t, then get S at 2 delta t, S at 3 delta t, finally you get S at final expiry t. But your distribution will not be exactly the same distribution as the stock terminal distribution, the geometric bounding motion, because every middle step, there is some discretization error. So to summarize, in method 1, we are directly simulating the exact stock terminal distribution. In the second method, we are simulating the whole path and can only approximate rather than exactly simulate the stock terminal distribution. In this video, I will mainly focus on the first method. I will try to use some Python code and graphs to show the convergence of Monte Carlo simulation. So before I do the coding part, let me emphasize the importance of Monte Carlo convergence for vanilla prices. Some people might be wondering why we would use Monte Carlo to price vanilla if we already have an analytical model which is more accurate and faster. Well, in practice, a lot of exotic options have very complicated structures like barriers, coupons, best of, worst of. Sometimes this complicated structure can degenerate to a simple vanilla. For example, for an up and out barrier, if the barrier is very high, then the payoff will degenerate to a vanilla. So in this case, the Monte Carlo price must match the vanilla price. Although for pure vanilla, we should use analytical Black-Scholes formula to give more accurate prices. Okay. Let me try to use some Python script to code a specific example. Here I define a Monte Carlo vanilla terminal script, which takes 7 arguments: call, put, spot, expiry, strike, interest rate, volatility, and number of paths. So the final argument is number of paths. So what I'm doing in this function is, so initially I generate the random numbers, which are number of paths of them. But I'm generating the random numbers using antithetic, which means I'm generating the first half by directly calling the random number generator. But for the second half, I am directly using the directly negative the first half to get the second half. For example, if number of paths are 1024, I will generate 512 paths using the random number generator. The next one, 512, will be just the negative of the first half. The reason why I can generate this way is we know standard normal distribution is symmetric, so this trick will help to generate more accurate random numbers. Technically, this is called variance reduction. So then after I get the random numbers, I calculate the final stock price distribution. So put the random number here and then times square root t times sigma, then plus r minus sigma square t, then do an exponential outside, then times spot. So this is the spot price distribution. Then I calculate the fair value, which is e to negative rt times, if it's core, it's s minus k. Otherwise, if it's put, then it's k minus s. Then I do some post-processing process. So firstly, I will divide the fair values by strike. This will normalize the fair value. I will try to show the fair value in percentage terms, because only percentage fair value makes sense. Then I do the average of over all the paths. This will give me the fair value that I want. Finally, I also need to collect a very important statistic info, which is called the standard error of sample average, which is calculated as the sample standard deviation divided by the square root of number of paths. This is a very important statistic info. It will tell you how accurate your sample average is. If this value is very small, that means your fair value is very accurate. Okay. Then I define the test function in this test blackshoes.py script. So here, firstly, I define the contract. It's a core option, spot is 100, strike 100, expiry is 1 year, interest rate is 2%, volatility is 20%. Then I calculated the Black-Scholes fair value. I'll try to use the Black-Scholes as my benchmark comparison to test how accurate my Monte Carlo simulation is. Then I will collect the information for a different number of paths. For each path, I will collect the fair value and the standard error, which are defined in the Monte Carlo vanilla terminal script. Then I will also collect two other columns, which are called error and paths. The error is just the fair value minus Black-Scholes fair value. So this is the exact error. Then also I collect the number of paths. I put all of them in data frame. Then print the data frame. Finally, I plotted a figure which is a log plot of the standard error versus the paths. So let's take a look at how the results are like. So Okay, let me run. Well, here's the result. This is the data frame. Collect all the information we want. So fair value, so it's initially 8.6% and finally goes to 8.9%. Standard error, you can see it's monotonically decreasing. This is the error, so it's also generally it's also decreasing. So and this is the paths. If you take a look at the figure, it's very interesting. You can see that the standard error and the number of paths, the log of standard error and the log of number of paths, actually they are almost on a straight line. If you take a look at the slope of this straight line, it's actually almost negative 0.5. So that is the convergence rate of the Monte Carlo simulation. So what we just got is the log of standard error is approximately 0.5 log of n. So if we do an exponential on both sides and do some math, we can find the standard error is approximately c over square root n. So the standard error is decreasing at a rate of square root n. So as your number of paths increases, your standard error will decrease. So your fair value will be more accurate. Okay, that's all for today's video. I hope you enjoyed. I'll see you next time.